Hello guys, welcome to my YouTube channel. In this video today, we are going to derive the key formulas for closed-coiled helical springs under a shear load, including the deflection, the shear stresses in the wire, and the strain energy stored in the spring. If you're studying, mechanics of materials, or preparing for an exam, you're in the right place. Make sure to like this video if it helps you, and also to subscribe so you don't miss out on more breakdowns like this. So let's dive in, guys. Now, springs. Now, we know that, or let me just give you a definition of springs. First of all, I recommend you to, use Rashput strength of materials to read if you want to look more into it. But there you go, springs. A spring is an elastic member. Please note the term elastic member. It's an elastic member that would distort under load application. Of course, when you apply a load to it, it will distort. And when you remove this same load, it must return back to its original position. Now, whatever way you put this definition, just know the key points: distorting, returning back to original position, and lastly, it's an elastic member. Now, let's go to the types of springs. We have helical springs. Springs can be helical. We have a leaf spring. We have torsion springs. We have flat springs. Now, of course, we can further break this down. Under helical springs, we have open-coiled. Forgive my phonics, guys. Open-coiled springs. We have closed-coiled springs. We have the compression springs, and we have tension springs. Under this leaf spring, because of space, I will dictate. Under this leaf spring, we have elliptic spring, that is full elliptic spring. We have semi-elliptic spring, and lastly, we have cantilever springs. So now, but for this video, we're going to be discussing closed-coiled springs. Let's dive in, guys. Now, closed-coiled springs. I'll be using this diagram to derive some fundamental expressions that we'll be needing as we solve questions in the chapter 14 of strength of materials, which is springs. That is, the chapter is springs. So let's, how would I draw this now? Okay, let me go here. Sorry, my drawing is kind of bad. I'm trying to draw a spring with all these things I'm drawing. Single things are called coils. They make up a spring. Sorry. then the weight attached to it is called. Now, here you go. Now, of course, when this spring is stretched, when it is stretched, we have length. That is length of spring. You get. And length of spring has a formula. The formula is L is equals to 2 pi r n. Don't worry, I'm going to explain. So, length of spring once again is equals to 2 pi r n. So, all these once again are called coils. All this, in fact, when you what's the term now? When this length is round, the number of the turnings are called the coils. So, and this coil is denoted as n. Please note the term n. Now, once again, I said in the definition that when load is applied to a spring, deflection occurs. Let me represent it in a diagram. But first of all, know that this is the notation of deflection. Let me represent it in a diagram. So, this is deflection. This is the radius of the coil. And this is the angle of twist. Now, there's radius of coil. There's radius of wire. These things that make up the coils are called the wires. We denote it as small letters. So if we're dealing with the radius of the wire, we denote it as R. If we're dealing with the diameter, which is 2 times the radius, we denote it by D, small letter d. But when it comes to coils, we denote it by capital letter, that is the number of turnings itself. If we're dealing with the radius of the coil, we denote it by R. If we're dealing with the diameter of the coil, we denote it by D. So, once again, let's move to our triangle. By the way, this is Mechanics of Materials 3, a 300 level course at the University of Lagos, what I'm currently offering this semester. So, write this down somewhere, note it down somewhere. Now, let's go back to our Mechanics of Materials 2, the torsion relationship. Torsion relation. So, we can recall that G theta over L is equals to, what is it again? Shear stress over R is equals to torque over what is it? Yes, G. Yes, guys. So, we'll be needing this expression. It's fundamental to us. So now, first of all, earlier in the video says we're going to be deriving. Now we need to derive the formula for shear stress. But before we derive, let me tell you what all these letters mean. G is modulus of rigidity. Modulus of rigidity. Let me write it here. Theta is the angle of twist. Length, like I explained earlier, is the length of the unwound wire. Forgive my handwriting, guys. tau is the shear stress. R is the radius of spring wire. T is what's the name? Is it torsion or is it torque? It's torque. Of course, it's torque. Since it's Newton's meters, Newton times meters, that is force times distance over 2. If you can recall in MEG, torque. J is polar moment of inertia. Guys, can you see how it's linking to year 2 when we did strength of materials, Abby, or rather mechanics of materials too? So now let me come to this J. If you can recall the perpendicular theorem in the moment of inertia, second moment of area, we looked at something like this. We did parallel axis theorem and we did perpendicular theorem. So IZZ in the perpendicular theorem is equals to IYY plus IXX. And remember, when we are dealing with springs, the cross-section of a spring is basically a circle. It's circular. So, and remember, the moment of inertia for a circular cross-section is equals to pi d4 over 64. So I can say that IYY is equals to pi d4 over 64. And I can also say that IXX is equals to this same pi d4 over 64. If these two are the same, it means that my IZZ, which is equals to my polar moment of inertia, which is equals to J, is equals to 2 times pi d4 over 64 because of this formula here. Since IYY is equals to IXX, which is equals to J is equals to pi d4 over 32. Note this, please. Now, we have our J. Let's derive the formula for our shear. Let's start with shear.